Hello, my name is Hunter Levinson, and this is my lab report for Physics 2212 on magnetic molasses. So this lab is going to be an analysis of the calculations that we received from a magnet falling through an aluminum foil wrapped around a tube or around itself, and the computational simulations of this experiment. Our initial conditions and assumptions are stated below, most notably that the length of the tube is 0.635 meters, the width of the foil is 0.0055 meters, and the inner radius and mass of magnet are here, and then we use the magnetic dipole moment from Lab 04. Our main results were that our average experimental time was 1.45 seconds, and the predicted time was 1.476 seconds, which obviously is very close. And we'll describe the disturbances in that time later based off our sources of error. So here are the fundamental principles. We have Faraday's law, which is, as you can see, which is going to calculate the magnitude of the change in flux over the change in time. Then we have the magnetic field of a dipole, which is K times basically the same thing for a charge, except for you replace the P vector with an M vector. Then we have the magnetic force on a wire loop, which is this equation right here. This cross product is really important. The EMF equation, which is the same thing as the change in flux over the change in time, so that relates to Faraday's law. And we also know, of course, that the EMF is equal to the current times the resistance. Finally, force of gravity is, as always, mass times gravity in the y direction. So our procedure was to mark N on the magnet, hold the tube vertically, start the video, drop the magnet through the tube, repeat 5 times, and then determine the time codes of it exiting and entering the tube, and use that to determine the average time of the magnet. Let's see. So that is the video of what occurred. Here's my computational model. Here are the values that I told you guys earlier, the mass and the mu mass that I told you earlier. Here's the equation for the dipole of the magnetic dipole moment or field, and that is the equation that we got before that I showed you guys. Then we have the d flux dt, and that once again is the equation that I showed you before. Gravity is negative mg, like we talked about before, and then the current once again is the resistivity times the current is equal to the change of flux. Next, we did these equations, which were able to determine the magnetic field at every moment. And then we plotted it, calculated F magnetic and F net by adding magnetic and gravitational. And as you'll see, that gave us this curve right here. So answering these observation questions, we knew that the red current must flow counterclockwise and the blue clockwise, since the direction of currents would create a magnetic field that opposes the motion of the magnet, which is what we would expect to happen. Then the system's dynamics should remain unchanged. The computational system does not take into account external magnetic fields, which is what causes the more variations and not as accurate. And then we kind of see that the accelerations, there's an imbalance, and they slowly begin to get equal and equal, which is the flattening of the curve, the change in velocity, until it exits at the very end. And we get the 4.476 seconds, as I described before. So our sources of error were the external magnetic fields, like we talked about, the TVs, devices like phones and tablets and stuff like that, all with currents passing through them, and power lines that are going through the floors to the walls, giving energy, light to the room and whatnot. Of course, the air resistance and friction, which we said we were going to say were negligible, and the non-uniform distribution of the aluminum foil, which definitely did play in. This aluminum foil was not made perfectly. It wasn't very well wrapped, so there were definitely problems with that. A small resistivity would have increased the current, and due to the conservation of voltage, that would have created a larger current and a larger magnetic field, which would mean that the ratio of magnetic field to gravity would have been much greater, or gravitational force, causing the magnet to move much slower. If you had holes in the ring, that would disrupt the flow of the current, making the magnetic field much weaker for every individual ring, and sometimes not even having a magnetic field for some of the rings, because they're discontinuous, and that would cause the magnetic to fall through much faster. So thank you very much. I hope this was well explained and you were able to understand it, and I hope you have a great day.